Hello everyone, this is the second class of this week. In the last class, we discussed how to construct element stiffness matrix for beam member, and then today we will see if for a given problem several members we have, and then we have constructed the stiffness matrix for different members, then how to assemble them to get the global stiffness matrix. That is the topic of today's lecture. So, today we will discuss the assembling of member stiffness matrices. Now, just before that, recall this we discussed in the last class. If you have a member connected between two nodes I and j, and the degrees of freedom at ith node is 1, 2 and degrees of freedom at jth node is 3, 4, then this is the stiffness matrix for this member, general stiffness matrix for this member. Now, what we have is this is, if you recall, this is your node number 1. This is for node number 1, this is for 2, this is for 3 and this is for 4, right. And then this similarly this is for 1, this is for 2, this is for 3 and this is for 4. So, and corresponding we can write these stiffnesses as K11, K12, Kn3 and K14. So, and we already discussed what is the physical significance of this K11, K122. Okay. So, let us move on, see how to do the assembling. Take an example first. Suppose this is the example we take. Now, we are not going to solve this example today. Instead, what we do is through this example, for the given problem, through this example, we will try to understand how to do the assembly. We have done this for truss problem, and we just discussed the same exercise for beam problem. So, first, but once we discuss everything, towards the end of this week, we will take up this example and then see how to solve them. Okay. So, the first thing is we have to discretize it. Once we have to discretize it like this. So, we have two members now, member number 1 and member number 2. Then we have the degrees of freedom is member number 1 is connected between 1, 2 and then 2, 3 for member number 2, and this is how the degrees of freedom are defined for different nodes. Okay. Now, so if we take member number 1, the corresponding member number 1, the stiffness matrix, suppose the stiffness matrix is this superscript 1 stands for, it implies that it is the stiffness matrix for 1, member number 1. Now, this is important, this numbering is important. You see here two figures are there, this is figure number 1 and this is figure number 1 and figure number 2. What is figure number 1 and 2? You see, figure number 1 is the definition through which we have derived the expression for stiffness matrix. Okay. Now, and in that definition we identified the ith point degrees of freedom is 1 and 2 and jth point degrees of freedom is 3 and 4. But you know, for different, but when the member, when we take a member from the actual structure, their actual degrees of freedom may not be 1, 2 and 3, 4, it may be different. Okay. So, but in these expressions, so the red numbering here you can see on the stiffness matrix, red numbering 1, 2, 3, 4, it is how the stiffness matrix is constructed, and then the blue one is how the stiffness matrix with respect to the global numbering. Okay. Now, for the member number 1, the global numbering and this idealized numbering, they are same, and therefore, these two are same. It will be when we see the next member number 2, this will be more clear. So, this is the stiffness matrix for member number 1. We are not writing the expression for the stiffness matrix like this, we are not writing this expression. The reason is we already know this expression. So, therefore, once we have the final global stiffness matrix in terms of K11, K12 and so on, we can substitute this expression for a different members. Okay. So, now let us do it for second problem. The second problem, this is the second member, this is the member number 1 and this is member number 2. Now, this is the difference. Red one, it is the numbering of the nodes while in the actual idealized system, but blue one is the global numbering. You see, member number 2 was between node number 2 and 3. Okay. So, node number 2 is I in this case. So, node number 2 is I and node number 3 is j. Okay. Now, in the global degrees of freedom, as per the global definition, the second node, the degrees of freedom we defined as degrees of freedom 3, 4 and the third node degrees of freedom 5, 6. Okay. Now, so but in the local when we write this stiffness matrix in this form, our degrees of freedom is 1, 2 here, 3, 4 here. So, the global degrees of freedom 3, 4 is essentially local degrees of freedom 1, 2, global degrees of freedom 5, 6 essentially local degrees of freedom 3, 4. Okay. So, essentially just to make it simple, if we the red numbering is with respect to figure number 1 and in the global sense when we actually assemble them, the corresponding these will be corresponding to degrees of freedom 3, 4. Similarly, these will be correspond to degrees of freedom 5, 6. Okay. Now, once we have these stiffness matrices for both the members, next is to assemble them. Now, the reason why we as I said just now the reason why we chose a problem with 2 span, because we can do the assembling on the screen, but for a problem where you have many spans and many nodes, many members and many nodes, then these assemblings you have to do using a computer code. Okay, so this is the degrees of this is the corresponding now this is the stiffness matrices written in terms of the it is identified corresponding rows and columns are identified with respect to global numbering. Okay. Now, so as you recall the first step of the stiffness, it is evident that you have total 6 degrees of freedom. So, essentially the stiffness matrix, the size of the stiffness matrix will be 6 by size of the stiffness matrix will be 6 by 6. Okay. Now, so first is initialize, we have to take a 6 by 6 matrix, all the elements of this matrix is 0. Now, next depending on their position, their connectivity, we have to populate this matrix, we have to replace 0 with their corresponding values. Now, first let us check with let us check this. Now, this is let us check blockwise. First, to make it clear, just remove all these zeros, so that yes. So, now all these are initial value is 0 now. Okay. Now, so this is for 1 1, right? This is for 1, this is for 1. Now, this is for 1 and this is for 1, there is no 1 1 here. So, straight away it will be k 1 1 1, okay, this value. So, this value is already given. Then we have k 1 2, one row and second column 1 and then corresponding will be 2, there is no here. So, this is k 1 2 1. So, we have taken this. Then k 3 4, k 1 3 4 1 and then 3 is this, there is no 1 3. So, it will be k 1 3 1 and similarly this will be k 1 4 1. So, this is we have already substituted this value, we have included this value in the global stiffness matrix. Then then 1 5 6, there is no 1 5 6 here, there is no 1 5 6 here. So, this will be 0 and 0. This was for the first column, first row. Let us see the second row. Second row, the first column is 2 1. We have 2 1, this is 2 1, so this will be k 2 1, k 2 1 1, this gone, it will be 1. Okay. Then k 2 2, k 2 2 will be this, k 2 2 1, this is gone. Then we have 2, then 2 3, 2 3, there is no other 2 3. So, this will be k 2 3 1 and similarly k 2 4 1. So, this is gone, this is gone. So, this will be 0 and this will be 0, right. So, this is for second row. Now, let us do it for third row. Third 3 1, we have 3 and then 1, this will be 3 1, this is 3 1, this will be k 3 1 1. Then 3 2 3 2, there is no 3 2 here, 3 2 will be this value k K321, then K33, here we have K33 is this, and then we have K33 here is this. So, K33 will be this plus this. So, this will be K331, this will be K331 plus this will be K11, K33, K112. Okay. So, these two. Then 3 4, we have 3 4 here and we also have 3 4 here. So, 3 4 here is this and then 3 4 here is this. So, this will be K341 plus K122, K341 plus K12, K122. So, this is for this. Then 3 5, we do not have any 3 5 here, we have 3 5 is this one and 3 6 is this one. So, this become K132, this becomes K132 and this becomes K14, K142. So, this is for the third row. Do it for this fourth row. Fourth one is this 4 1, there is no, yes, there is 4 1 is here, 4, then we have 1, this is K41, we do not have 41 here. So, it will be K411 and then K4 this gone, then K421 is this, K421 is this, K43, K43 what we have K4 and then K3, here also we have K4 and K3, K43 is this one here and K43 is this one here. So, this will be K431, K431 plus 43 K222, then it will be K431, K21, K21 2, this will be 1. Okay. Now, let us do it for then K44, K44 is this one is K44 and then K44 is this one. So, K441, K441, small K441 and this case it will be K222, K222. This is for K44. K45, there is no K45 here, K45 we have this is K45, K232, K232 and K46 will be K242, K242. This is for K, this is for the fourth column, fourth row. Now, similarly, let us do it for I can put it here, yes, that is better. Let us do it for fifth column, fifth row. So, 5 1, there is no 5 1 here, there is no 5 1 here, 5 1 straight away will become 0. 5 2, there is no 5 2, 5 2 straight away we can have 0. Then we have 5 3, 5 and then 5 3 is K312, K312. Then 5 4, 5 4 will be K322, K322 and then 5 5 will be 5 5 will be K332, K332 and finally 5 6 will be K342, K342 and then last row 6 6 1, there is no 6 1 here 0, there is no 6 2 here 0 and then 6 3 is this K412, K412, 6 3 6 4 will be K422, K422, 6 5 is K432, K432 and 6 6 finally is K442. So, we have taken all these elements and substituted here. So, this is now our global stiffness matrix. Okay. Now, look at global stiffness matrix is symmetric or not. It is symmetric. K12, this K121 and K21, K121, K21, these are stiffness, these all the these stiffness matrices, member stiffness matrices are symmetric and then global stiffness matrix is also symmetric. And but you know, when you write the computer code or when you do this assembling manually, you start with writing all the, though you know that this is a symmetric matrix, do not take it for granted for the time being when I say do not take it for granted, what I want to mean is, when you write the stiffness matrix, write each component separately and then check whether the stiffness matrix is symmetric or not. That would be a check whether your assembling is done properly or not. Okay. Now, so this is the global stiffness matrix. Now, let us write it. Let us see the final form of the global stiffness matrix. So, for this member, the global stiffness matrix is this. Remember, this is the stiffness matrix written in terms of K1, 2, K2, 3 and so on, but we know what is the expression of different components in terms of length, in terms of flexural rigidity. We will do that. We will substitute those values here and get the global stiffness matrix when we actually solve this problem. But as I said, here our purpose, our objective has not been to solve this example. Our objective has been to see how the assembling is to be done. Once we have understood that how the assembling is to be done, the next when we actually solve them, we will write all these values in this assembled stiffness matrix and then solve it. Now, for the solution, we have done the first step, discretization. Second step is member stiffness matrix. Third step, assembling the stiffness matrix, which give you global stiffness matrix. Then the fourth step required is the boundary conditions and the load vector. This stiffness matrix will be the determinant of this stiffness matrix will be 0. You substitute all these values and find out the determinant, you will see this is 0. The next step is to construct the load vector and apply the boundary conditions. That will be the topic of the next class lecture. So, next class we will see how to enforce boundary condition and how to construct load vector. So, I stop here today. See you in the next class. Thank you.